Hello everyone. Today I'm going to give you the application of rich representation theorem for Hilbert spaces. Okay, so first of all, let me state rich representation theorem. So here, theorem, so which is called rich representation theorem. Okay, so let H be a Hilbert space. Hilbert space. Then for any L is in L prime. So L prime is dual space of H prime, and there exists a unique U L is in H such that one Lx equals to UL and X. Okay, this is for any X in H. And second property, the norm, operator norm, L1, L norm is the same as norm of UL. Okay, so this is H1 norm, this is H prime operator norm. So this is a very important rigid representation theorem. So I'm not going to prove, but this is in our textbook. And today I'm going to, and then we have another theorem. From here we can also have the adjoint operators. Okay. So what is adjoint operator? So we know that in theorem 2, so adjoint operator let H1 and H2 are Hilbert space, be Hilbert spaces, and I take L is operator from H1 to H2, be bounded linear operator, then there is a unique bounded linear operator which is called H star, is from H2 to H1 such that so inner product X and H star Y equals to this one is in where? So H star, this H1 inner product, and then HXY is in H2 inner product. Okay. And furthermore, this is a hold. Also, we can prove H star L. Oops, I'm sorry. This is not H. This is let me change this. This is not H, so it looks strange. L star. This. Okay. That would be L star LX. Okay. and satisfy also the norm of L star norm is the same as norm of L. Okay, so this is what we have. So here, L star is called the adjoint operator. So the adjoint of L. So adjoint operator of L. Okay, this is definition. Okay, so this is very important theorem. So one is Ricci representation theorem, and we have adjoint operator. And then we have one more theorem I want to address, and another. Let me call this is a theorem A. So this is theorem B, and then I will have this one is theorem C. So here let H1 H2 still are improper space in L is operator from H1 to H2. H1 to H2. This is Hilbert space. This one is a bounded linear operator. Bounded linear operator. Then, so we have following properties. First of all, the range of L. So the range of L closure is the same as a kernel of L star orthogonal. Okay, this is one. And then second one is kernel of L equals to range of L star orthogonal. So this is what we have. Okay. Yeah. So let's try to prove this statement. So proof. So this will be very important application in the future. So we like to prove the statement over here. Okay, first one. So let's see. First of all, we want to prove is this. Okay, so you take for part A, for I take for any element Z is in range of L. Then there exists X is in H1 such that because Z is in the range, then Lx equals to Z, right? So we have that one. Then first we want to prove what we want to do is Z is in orthogonal. So first we want to compute this one. So Z and Y. Okay, so let's take then for Y is in kernel of L star. Okay, so L star is from H2 to H1. Okay, I take an element in here, Y kernel. So and then I compute Z Y. Okay. So by definition, this is L Z equals Lx Y, and L star the adjoint operator. So this is X L star Y, but Y is an element in kernel, so this equals X0. Final we have this is 0. Okay. So what we have is this. That implies that I take for any element in here, this one is orthogonal to element here. So what we have here include that the range of L is in subspace of kernel L star orthogonal. Okay. Yeah. And you will see this guy kernel here, since kernel of L star orthogonal is closed. This is closed subspace. Okay, so that implies RL closure is a subspace of RL closure is subspace of a kernel L star orthogonal. Yeah, that's what we have. Okay. And so that I have the range of L closure subspace of a kernel L star orthogonal. Okay. So on the other hand, let's now for I take Z is in R range orthogonal. I take over here. So range orthogonal. So range of L is in H2. Then I compute so for every, then I compute L x Z H2. So for any x is in H1. So this one is an image. G is orthogonal, so that should be always 0. That is equals x times L star Z. Okay. So this one has to be H1 inner product. Okay. So this is 0 for every, so that implies what? X inner product with L star Z H1 inner product always 0 for every X in H1. Okay. And then by property of inner product, the L star Z equals 0. So that implies Z is in kernel of L star. Okay, that's what we have. So that implies what? So I take for any element in range of L orthogonal that is in kernel L star. So we have a range of L orthogonal is a subspace of a kernel of L star. And from here, then you take orthogonal both sides, then kernel L star orthogonal is a subspace of a range of L orthogonal to orthogonal. So that's what we have. Okay. Then now you see that we want to prove that. Next we want to prove that this one equals to range of L closure. Okay. So once we prove this one, so we are done. In fact, RL orthogonal to orthogonal is the closed, the smallest closed subset that include RL. Okay. Why this is true? So here, okay, I want to prove this one. Why is this is true? Well, you know that the range of L is always a subspace of a range of L closure. Okay. Then RL closure orthogonal subspace of RL, orthogonal. Okay, and then RL orthogonal to orthogonal, orthogonal is a subspace of RL closure orthogonal to orthogonal. Okay. Here, here. So when this is closure, this is closure, this is closed, then this is RL closure. This is the same. Okay. So here, here what we need is the V is H. Suppose like H enclosed. Then V orthogonal to orthogonal is V orthogonal. The why this is true? This is H is Hilbert. So H is Hilbert. Then you have this. If this is closed, then you have a V. Inner direction is V of this one, right? V over that one. And also you can have another expression V H equals V orthogonal, and then inner direct sum is V orthogonal to orthogonal. So this uniqueness, you can have V should be the same as this one, right? So you can actually prove, not difficult to prove this statement over here. Yeah. Yeah, I can show you this is immediately. This one holds immediately. So this is true. Yeah, this one is true. Okay, well, this is it. This is what we partially proved. So this is true, and finally we proved A part. Okay. So we proved A part, and for B part you replace. You can use L and L star. So V B follows from A by replacing L by L star and L dual adjoint would be L. So using this fact, so we can prove easily. Okay. Yep. So now, I didn't keep you. Oh well, you can prove this statement. By yourself. for this case, let's see. Let me give you some proof of this part. Okay, this part. So how do I prove this one? Clearly, V is subspace of Y orthogonal to orthogonal. Yeah, by definition, this is not Y, V. This is by definition of orthogonal. You can easily show this is true. Very easy to show each fact. And the other part, so you only show the other way around. So let's take any element. So let's take 4. X is in V orthogonal to orthogonal. Okay. Then you have H, whole space H is V orthogonal to V orthogonal, right? V direct sum with V orthogonal, because V is closed, you can write it in that way. So X is in H, so X you can write down Y plus Z, where Y is in V, Z is in V orthogonal. Okay, and then in that case, this is direct Y and Z inner product equals 0 because they are orthogonal each other. So then I compute X and Z. So X is in V orthogonal, right? So look at here. Z is in V orthogonal. X in here. So they should be 0 by definition. Okay. And then I replace X by Y plus Z and Z. Then this would be Y comma Z inner product, and then I have a Z inner product of Z. So then we know that Y and Z are orthogonal. So this is 0 plus, and this one is Z norm squared. So finally what I have, Z norm squared equals 0. That implies Z equals 0. So hence X should be Y. Y is in where? Y is in V. Okay. So that implies what? I take for any element X is in V orthogonal to orthogonal. X belongs to in V, right? So V orthogonal is in V. Okay. So the other way is very easy to check. That's how you to prove this statement. Okay, and next, I'm going to introduce a very important theorem. So it is called Lax-Milgram theorem. It is very important to prove the existence of solutions. Okay, so what is Lax-Milgram theorem? So here, the theorem I want to give you here is theorem CD. So it's called Lax-Milgram theorem. So we consider the following some problems. Okay, so I have let A is in V, H, V cross H cross to H. Let's call Hilbert space. So V cross V to R be a bilinear form. Here V is a real Hilbert space. The real Hilbert space. And V, you know the bilinear form. So linear, when you fix the one component, one variable is linear. And such that, so we have following two conditions. The first condition, A is continuous. So bilinear form is continuous means what? That means there exists some m is positive such that A uv absolute value of this one is less than m norm of u and norm of v. So for every uv is in v. Okay, this means A is continuous. And then second property is coercive. It's called coercive. So A is coercive. Coercive. So that means what? That means there exists alpha is positive such that A, you take the same element, AVV is greater than alpha norm of V squared for every V is in V. So it's called coercive. Okay. Okay. Then what we have, so then for H is in H dual space. Okay, H prime dual space. F in dual space. That there exists a unique solution. So there exists. It's a little bit generalized Rich representation theorem. So there exists a unique solution U bar is in V such that A U V equals to F V for every V is in V. Okay, satisfy this condition, and also satisfy U bar norm is less than or equals to 1 over alpha F norm. F is in V prime norm. Okay, this is not H, this is V prime. So dual space, okay, V norms. Okay. The Rich representation, it looks like the Max-Milgram theorem is a little bit different form of Rich representation theorem. So basically, we use Rich representation theorem. And when you look at the AUV, this one is actually the weak form of some equations. Okay, so existence of some equations follows, many of them follows Lax-Milgram theorem. So I'm going to prove this Lax-Milgram theorem next time. Okay.